Hello students, welcome to experiencetutor.com. Today's lesson is Class 12 Physics Electrostatics Part 7.
Let us start with the welcome message. Dear students, welcome to our channel experiencetutor.com. In this channel, we will teach physics, chemistry, mathematics and biology for the students of class 10th, 11th and 12th and those who are appearing for the school board examinations and entrance examinations like IIT, NEET and all state level engineering and medical examinations. This course is organized according to different topics for each subjects. Therefore, it contains separate video for each and individual topics. Hence, it covers complete syllabus for CBSE, ICSE, ISC and all the state board examinations and engineering and medical examinations. You can also find the relevant topics for foreign school examinations like SAT, IGCSE, IB, etc. Enjoy your learning. Thank you.
Question number 42. Find the force acting on a charge Q placed at point P due to surface charge distribution. As shown in the figure, suppose the charge is distributed continuously over a surface. We want to determine the force on the charge Q placed at a point P having position vector r due to this charge distribution. Here the charge is distributed continuously over a surface having a surface charge density sigma, position vector r dash. Surface charge density is the charge per unit area. Sigma is equal to total charge on the surface upon surface area is equal to Q upon A. Unit of sigma is coulomb per meter square. Imagine the entire surface to be divided into large number of small surface charge of dA dash. The charge in area element dA dash will be dQ is equal to sigma r dash modulus dA dash. Force acting on charge Q due to this charge dQ will be dF is equal to K Q dQ upon r modulus of r upon minus r dash whole Q multiplied by r minus r dash. R and r dash are the position vector. The total force on Q due to the charge on the surface can be determined by taking the surface integration of above equation. From equation 1.8.5 and 1.8.6, force is equal to surface integration dF is equal to KQ surface integration sigma r dash modulus dA dash upon modulus of r minus r dash ka whole Q multiplied by r minus r dash. If the charge at point P is very small, then electric field at that point E is equal to F by Q, putting the value of F is equal to K integrations sigma r dash modulus of dA dash upon r minus r dash whole Q multiplied by r minus r dash. Question 43. As shown in the figure, a square having length A has electric charge distribution of surface charge density sigma is equal to sigma naught xy. Calculate the total electric charge on the square. The Cartesian coordinate system is shown in the figure. As shown in the figure, consider an element of charge dx dy at a point xy. The charge on the area element is dq is equal to sigma naught xy dxy. Therefore, the total electric charge on the surface is q is equal to sigma naught integration from 0 to a x dx into integration from 0 to a y dy. On solving, we get sigma naught x square upon 2 uh, 0 to a and y square upon 2 0 to a. On solving, we get dash sigma naught a square upon 2 a square upon 2. Therefore, q is equal to sigma naught a to the power 4 upon 4. Question 44. Find the force acting on a charge q placed at a point P due to the volume charge distribution. As shown in the figure, suppose electric charge is distributed continuously over some volume and volume charge density is rho position vector r dash. Volume charge density is charge per unit volume. Therefore, rho is equal to total charge upon total volume, which is equal to q upon v. Unit of rho is coulomb per meter cube. Imagine the entire volume divided into small volume element dv dash. The charge in this volume element will be dq rho r dash dv dash. Force acting on the charge q at point P having position vector r due to charge dq will be df is equal to kq dq upon r minus r dash whole cube r minus r dash. As explained earlier, the total force acting on charge q can be determined by taking volume integration of above equation. F is equal to volume integration of df, which is equal to kq integration of volume integration rho r dash dv dash upon r minus r dash whole cube multiplied by r minus r dash. If charge q is very small, then the electric field at point P will be E is equal to F by Q is equal to K volume integration rho r dash dv dash upon r minus r dash whole cube multiplied by r minus r dash. Question number 45. What are electric field lines? Explain the electric field lines of a dipole with a diagram. Electric field lines are the pictorial representation of electric field produced by electric charge. Scientist Michael Faraday introduced the concept of electric field lines and obtained important results of electric field. Faraday called this electric field of lines as line of electric force. An electric field line is the curve drawn in an electric field in such a way that the tangent to the curve at any point is in the direction of the net electric field at that point. In fact, an electric field line of field is the path along which positive charge would move if free to do so. Now, we consider an example of electric dipole understanding the method of drawing electric field lines. We can use the equation of electric field lines to determine the intensity of the electric field at any point. As shown in the figure, drawn a vector of electric field E1 at a point P according to the magnitude of and direction at electric field at that point. Now consider another point P dash close to P and draw a vector of E3 at point P double dash very close to P dash. Same way other vectors of electric field can be drawn. P, P dash, P double dash are these points. All these points are so close to each other that a continuous curve passes through the tails of this vector can be drawn. This curve presents the electric field lines. Thus, the curve on which the tangent drawn at different points like P, P dash, P double dash and so on represents the direction of the electric field at respective points is called electric field line. Question number 46. Give the characteristics of electric field lines. First, electric field lines starts with positive charge and ends at negative charge. Second, the tangent drawn at any point on the electric field line shows the direction of the electric field at that point. Third, two field lines never cross each other. If two lines intersect at a point, two tangents can be drawn at that point intersecting two directions of electric field at the point, which is not possible. Electric field lines of stationary electric charge distribution do not form closed loops. Fifth, the separation of neighboring field lines in a region at electric field indicates the strength of the electric field in that region. In practice, the number of field lines are so restricted that the number of field lines passing through unit cross-sectional area about a point get perpendicular to the electric field lines is proportional to the intensity of the electric field at that point. If the field lines are close to each other, the electric field in that region is relatively strong. If the field lines are far apart, the field is weak in that region. From the figure, it is clear that P1 electric field is relatively strong electric field at P2. Here in the first figure, we can see that Q is greater than 0, where electric field lines are coming out from the positive charge. Q is less than 0, showing that electric field lines are moving towards negative charge. Third figure shows the dipole where electric field lines are moving from positive to negative. And in the fourth figure, we can see that electric field lines are coming out of positive charge. Sixth, field lines is uniform. Field lines of uniform electric field are mutually parallel and equidistant.
And this is the end of this topic. If you like this video, please subscribe our channel and give us a like sign. Please click on the bell icon so that you get automatic notification when a new video is uploaded by us. Thank you for watching our channel.